Good day, everyone. This presentation is about programmable interface board for higher CubeSat form factor and complex mission payload. I am Marloun Sejera, doctor student under Laboratory of Lean Satellite Enterprises and In-Orbit Experiments or LASIN in Kyushu Institute of Technology, Fukuoka, Japan. Let me first provide a brief background of BIRDS project. The Joint Global Multi-Nation Bird Satellite Project, acronymed as BIRDS Project, is a cross-border interdisciplinary CubeSat project hosted by Kyushu Institute of Technology in Japan. The project aims to successfully build and operate first satellite of non-space-faring countries and advance towards indigenous space program in each country. Members of the project get to experience how to design, build, test, and operate 1U CubeSats in 2 years. The project began in 2015 and is currently in its fifth batch of participants. A total of 13 countries have participated in the project, 9 of which built their country's first satellite. The figure shows the internal structure of the BIRDS platform. The platform uses a backplane interface to connect the satellite's subsystems and payload. This greatly reduces the use of harness, which is considered as one of the causes of satellite failure. The backplane uses 50-pin female connectors instead of the conventional 104 pins in a PC104 style CubeSats. These smaller connectors consumes smaller space, which in turn provides more space that can be utilized by the subsystem and the payload. Finally, the backplane approach makes satellite assembly and disassembly very easy. This in turn makes integration as well as troubleshooting faster. The left side figure shows the top view of the backplane. The right side shows its bottom view. There are six 50-pin female connectors. Four of those are for subsystems and two are for mission payload. There are four 2-pin connectors for deployment switches and five 12-pin male connectors. The 12-pin male connectors, four of which can be found on the sides and one at the bottom of the backplane, are used to connect the panels to the backplane. At the bottom of the backplane, you can find the CPLD. CPLD is short for Complex Programmable Logic Device. This IC chip is programmed through JTAG. There are digital pins in the board connectors that are connected to the CPLD chip. The CPLD chip is used as signal follower, which connects a digital pin of one board, say onboard computer, to a digital pin of another board, say a payload. In this sense, the CPLD acts as the digital interface between the system bus and the payload. The same backplane can be used by another project with a different payload by reprogramming the CPLD to route the digital connections between the subsystem and the new payload. This gives the backplane flexibility to be used in different projects with minimal change in its design. This software configurable backplane was first used in one of the BIRDS 3 satellites and has been proven working in space since the satellite deployment on June of 2019. The next step now is to make use of configurable backplane on bigger CubeSats. The graph on this slide shows nanosatellite launches by types from 1998 up to 2025. What is evident in the graph is that most of CubeSat launch opportunities are in 2U, 3U, and 6U platforms. Thus, there is a need to demonstrate the configurable backplanes are scalable to higher CubeSat form factors. A 6U research CubeSat is under development in QTech. This CubeSat project is a product of collaboration between academia and private sectors. The CubeSat is divided into three sections. A 3U section is allocated to the high-resolution camera for Earth observation. A 1U section is allocated to Payload for technology demonstration and scientific experiments. Finally, a 2U section is allocated to Main Bus System, and which is based on Bird's 1U standard bus system. The three sections are interconnected through a backplane. The figure shows the configurable backplane of the 6U CubeSat. There are 12 50-pin female connectors. 6 are for the main bus and 6 are for the 1U payload. There are 3 2-pin connectors for deployment switches and 3 male connectors for the external panels. At the bottom side of the backplane, you will find the main bus CPLD. It is the same CPLD used by Bird's satellite. The main bus CPLD provides 22 digital connections within the main bus. These connections are comprised of DIO, UART, and SPI lines. A dedicated CPLD is also allocated for the 1U payload. It is used to route the digital signals within the payload. A simple VHDL code is used to program the CPLD as shown at the right side of the slide. The code is basically a voltage or a signal follower for all the 22 pair of connections. A portable logic analyzer is used to verify the input and output signal pairs. As shown in the left side of the slide, there is no significant delay on the input-output signals. The satellite was tested under vacuum conditions for about 60 hours, with worst hot condition of plus 60 degrees Celsius and worst cold condition of minus 15 degrees Celsius. Test results shows that the satellite operate normally at both worst temperature conditions. The satellite was also subjected to vibration tests to verify that it can withstand launch vibration environment. The table shows the QT levels used during the test. The result shows that no distortion or damage were found on the satellite. After conducting the functional check, there was no malfunction after the vibrations. As a summary, a backplane was designed to demonstrate the scalability of programmable interface board. It is used in a 6U CubeSat, which houses a 3U camera payload, 2U main bus, and a 1U payload. Complex Programmable Logic Device, or CPLD, ICs were used to route digital lines within the backplane. CPLD has flight heritage from the BIRDS project. The satellite passed space environment tests. And finally, the satellite is targeted to launch by end of the year. There is also an ongoing study on platform-to-payload interface where BIRDS project 1U CubeSat is used as reference. In this reference, the bus subsystem like OBC, EPS, and COM are integrated to the mission payload using backplane. The reference makes use of CPLD between the OBC and the mission payload. The CPLD can route digital communication lines from OBC to mission payload. This allows reuse of backplane on different mission payloads and avoid redesign. This reference has flown and proven working in space since the launch of BIRDS 3 satellite in June 2019. However, the reference is limited to same digital connections between bus and payload. and digital connections were limited to UART and SPI. From the survey collected during the 2019 Lean Satellite Workshop held in Tokyo, satellite developers foresee to use digital communication other than UART and SPI. These include I2C, CAN, USB, and others. Also, there is a need to integrate bus and payload that use different digital communication. From there, the ongoing study is focused on the design of a CubeSat interface that is able to route electrical connections between platform and mission payload, capable of handling communication protocols needed by satellite developers, and capable to bridge platform and mission payload which use different communication protocols. Lattice Semiconductor's MAC X02 FPGA was chosen in the study. The said FPGA is low power, similar to CPLD, and can be used as interface bridge, which is needed in the study. Reference designs of the interface are available on its website. So far, it is verified that the FPGA can work as signal follower similar to Bird's CPLD. The researcher is currently doing debug on the bridge code. This ends the presentation. Thank you for listening.